Well, I have time to work on problem 6 before starting making my dinner. The first reaction is, how on earth are we going to be able to compare these guys? But then I realized that this is formula 3 in the section. I'll just write it up. Actually, I didn't remember it by formula 6, but by the proof of the theorem in the section. They used it when they should do it with chi2 and chi4, where this was the two other were chi4. So my idea was to find the relation between these two guys. So that's basically what we are doing. So this one, let's work on that. And then we want to have jx out, j chi, so it's g chi2, and then we need one g chi, and g chi squared, and then we have this guy, so let's just check. This gives gx squared. That's not good. Divided by gx squared. Oh yeah, that's good. Gx squared is what we have here. And then gx up here, that's also there, so it shouldn't be here. gx22. I did it. Oh my God. So we have this gx2, gx, and then we multiply by gx. No, what do we do? This is annoying. This is really annoying. So we need to have dx squared. So we get that by dividing by it. We have d chi squared. And we have this already. And then we have that one, that one, that one, right. And then we want g of chi squared down here. Then we need to multiply by it. And then these two give j of chi with chi. Does this remind anything what we are dealing with over here in the proof? There was something with yeah. Well, I can't see I can use any of the formulas 2 or 3, so we'll have to work on the numerator and denominator. It doesn't look like we're in much luck, because here we only have the same function values multiplied by each other, and here they are coupled, chi of A, chi of B. So psi of x plus y. I can't get over this problem that they are taken by distinct elements here, and here they're taken by the same. So whatever transform I'm making, I can't get them to be taken by different guys. What they could do in the proof was that this was a character of order 2. Now they actually had the product of the character here that if that was the character 4 on character 2, then that was just the conjugate one. Uh-oh. But that was because changing sign on I, and it would only be negative if this was plus minus I, the square root minus 1. So therefore this would be the conjugate. But that doesn't hold in general. Well, time for a break. Hi. So, November the 8th, the day after the first part, and I wanted to work a little on the problem 6. We know that these are plus minus square root q, so that means that this equals plus minus dA of chi. So it's just a matter of deciding when it's plus and when it's minus. When I say just, that doesn't mean I can do it. One thing that solved the problem for us in the book was that this turned out to be if it was chi4, the character of exact order 4, then this would be the complex conjugate of chi itself, and that's solved the problem. Then this could be computed. We don't know that now, but at least I would like to think a little about the order. What could possibly be the order of this guy, and also of chi squared. If the order of chi is n, it may either be odd or even. And when we multiply it by, what should we call it, chi mark equals chi times chi 2, if we put this to nth order, that was the order. So chi to the nth is unity, and then this guy is chi 2 when n is odd, and 1 if n is even. So that means that in the case n is even, the order of chi mark is smaller than or equal to n. So could it be that some lower power gave unity? Goes to the nth. And if m is even, it's chi to the mth, and if m is odd, then it's chi 2. Can they actually be alike? So chi 2 equals chi to the nth chi 2. So if they are alike, it means that m is a multiplum of n. In particular, that m is larger than or equal to n. Now, what were the prerequisites here? didn't write that. Here we have m is odd. So in this case, chi to mth what I want to show is that the order of chi mark equals 2n. And we already have this, and then n itself if n is odd and we put it to n, then we get chi 2 So it's obviously that when we take chi mark to 2n, then it gets unity. So I have to prove that no other in between. Oh, that's because of this one. When it can't be m itself, then the next possible one is 2m. So that's the first result. When n is odd, then the order of chi 2 equals 2n. So when it's even, we already have an example, chi 4, of order 4, and the order of chi 4, chi 2, that was chi 4 conjugate, is 4 as well. On the other hand, if we take x mark here and then multiply, that has an even order. And if we take that and multiply x mark with x, then we get chi with chi mark with chi. That's chi times chi multiplied by chi 2, of course, chi 2 times chi 2. That equals just chi. So the order of x mark, chi mark, chi 2 equals the order of chi, which was n. So here we halve the order. The order is halved. So I claim so how can we distinguish that? it's a little weird. Let's try and put chi mark to the m-halves power. This obviously equals chi2 because the squaring it just gives chi to mth, which is unity. So now I can see it, m even and m odd. In case m is even, oh no, it's more complicated than that. Of course m is even, that's the prerequisite. So it's m halves being even, that's 4 divides m. Then this is even, so this is chi2. And when 4 fails to divide m, then this is odd, so we get chi2 to an even number, that gives unity. So now we have the condition. And it turned out to be exactly as I said. All right, so the order of and that's exact order, of course. So case 1, m odd. Oh, I've done that at all. Yeah. And here we have two cases, 4 divides m, in which case the order of chi2 equals that was now where are we? I just have to think it through again. The idea of doing it like this is that I think it all through once again. Then the order is the same. That's chi4 we had, yes? All right, that was what I'd hoped to derive something along these lines. I don't know if it will help us with the original problem, but that was it for now. I may be working a little more on the problem after my coffee break. Hello. Winter has come to Denmark with temperatures close to 0 and that degrees centigrade and humid weather, so it feels very cold. Ooh. I've been working on problem 6 without solving it. I've been stuck working on the numerator and denominator here. And one thing I tried was, of course, reducing this a little and then saying, okay, let's check this, the values of a, b, point a plus b. And having a result of the map, let's see if we can go back. And that gives, we multiply the last equation by a, we get a squared minus ay plus ab. And that's the second order equation, second degree, a quadratic equation. And the discriminant is given by this. So we have two solutions if this is 1, and if it's naught, then we have 1. So that means the number of solutions when going backwards is 1 plus chi2 of the discriminant. It's just a question of inserting the ab psi of a plus b. Then we get chi of x and psi of y. But then x2, that actually requires taking the square root b to get the value of b. So we could actually get it from here. Let's try that and see what we get. That's x, chi of x, psi 2 of b. No, we don't get it. We have to actually to solve it and take the square root of d. So there's no hope. So I worked on both of these, trying various stuff and not being able to do it. Then I peeked in the back of the book, and it appeared that we have to work directly on dA of chi with chi. So this is the guy we need to work on. And again, we have the map. Oops. A maps to a minus a squared, which we call y. That's a second order equation. With discriminant 1 minus 4y. And that means that when we have y, we already know the discriminant. Oh, it's still difficult to go backwards, isn't it? A itself equals 1 plus minus square root d halves. Well, let's see if we can, what we can do. So we'll sum over the values of this guy with their multiplicity. And the multiplicity, that must exactly be as before. So that is, we have actually the multiplicity as a function of y itself. So if you now do it like this, the sum chi of all t times the multiplicity of t, it seems to be y. And can we now sum over all y's? If this is naught, then it's naught or 1. And if y is a 1/4, that seems right. So this seems to be equal to j chi with chi. So let's expand. Now the map x maps to 4x is 1:1 because the character is distinct from 2. So we can actually just substitute. Oh, now what do we do here? Yeah, this vanishes, of course. And then we put 4 in here and takes 1 divided by chi of 4 outside. So that's 1 divided by chi of 4 times j of chi 2. So I made it far more complicated than it was. So I can see why I didn't consider it a very difficult problem, but not getting I was thinking in complexities. I wanted to do it all very complex and look like the first exercises doing all this. There you go. But now we've solved it, though not without help.